Hello everyone and welcome back to our course and actually to the last lesson of our calculus journey. Today we unveil the power of tangent lines as we use the Newton-Raphson's method for finding roots of nonlinear equations. Let us consider a function f which is continuous in a closed interval a, b, and differentiable in the open one. Then, if that function satisfies that f of a times f of b is less than 0, or in other words, f of a and f of b have different signs, then by the intermediate value theorem, we can assure that there's a value c in the interval ab such that f of c is equal 0. For instance, let us consider the function f of x, which is equal to cosine of x minus x. Notice that this function is both continuous and differentiable in the whole real number line. But let us consider only the interval minus 5, 5. Now, f of minus 5 is approximately 5.28. And f of 5 is approximately minus 4.71. As f of minus 5 times f of 5 is less than 0, we can use the intermediate value theorem for assuring that there must be a value c in the interval minus 5, 5 such that f of c is equal 0. Thus, c represents a root of the function f of x. A natural question arises: how can I find the roots of this function? Well, this is where the Newton-Raphson's method comes as handy by following these iterative steps. First of all, we take a value x null, for example, x null equals 3, and we find the equation of the tangent line of f of x at the point x null, f of x null. By using the derivative of f and the point slope equation, we find the tangent line of f at the point x null, f of x null, which can be represented as g of x equals f of x null plus f prime of x null times x minus x null. In our case, we have the following result. But let's keep on working on the general case. Now, let us consider a root of this tangent line, and let us call it x1. Now, as this is a root of the tangent line, then g of x1 must be 0. Thus, if we substitute x1 in our tangent line equation, we get that f of x null plus f prime of x null times x1 minus x null is equal 0. And if we solve for x1, we get that x1 is equal to minus f of x null divided by f prime of x null plus x null. We repeat the process, but substituting x null by x1 for finding another value x2, which represents a better approximation than the previous values that we found. And the iterative process provides the following values when we take x null equals 3 for our original equation f of x equals cosine of x minus x. And these are the values that we get. X null equals 3, x1 equals minus 0.4965, x2 equals 2.1310, x3 equals 0.6896, x4 equals 0.7396, and x5 equals 0.7390, which is a great approximation of the root of the function. In general, if we have a function f and we pick a value x0 for our iterative process after assuring that this function has roots, then our iterative process goes like this. X sub n equals x sub n minus 1 minus f of x sub n minus 1 divided by f prime of x sub n minus 1. And the limit when n goes to infinity of this iterative process provides us exactly the value of the root. Now is your turn to use the Newton-Raphson's method for finding the roots of the following functions. Try to use the intermediate value theorem for assuring that these functions have roots. Be proud of yourself for finishing the course. I hope you found it useful and that you learned a lot from it. I hope to see you in the next course.